Okay, the next section is optical activity. Basically, in this section, we're going to be looking at a property of chiral molecules that can differentiate one enantiomer from the other. Very important here, when you have two enantiomers, when you had our two molecules that we started with that are enantiomers, non-superimposable mirror images of each other, if you separated them and had a container with only the R enantiomer, such as R2-butanol, and then a container with only S2-butanol, what you would find is those two containers, R2-butanol and S2-butanol, have the same melting point. Whatever 2-butanol melts at, it doesn't matter if it's the R or the S, it's the same melting point, the same boiling point, the same solubility, the same IR spectra, the same densities. All right. The two enantiomers are identical in almost every aspect. There are only really two differences that we can measure, that we can see between the two enantiomers. One, they react differently with other chiral molecules. So if you're going to react R2-butanol with a chiral molecule, it will react differently than S2-butanol will react with that. And by the same token, it will have different solubilities if you are trying to dissolve it in a chiral solvent. So the first difference between these two enantiomers, one is they react differently with other chiral molecules. The best analogy to this is hands. Hands are chiral. Your left hand is chiral, your right hand is chiral. If you've ever played baseball or softball, you know that if you are a right-handed thrower, then your glove needs to go on your left hand. Note that a glove that goes on your left hand absolutely does not fit on your right hand, because your left hand is chiral. It has handedness. It's a hand. So your left hand is chiral. Gloves are also chiral. Baseball and softball gloves are also chiral, meaning you can get a left-handed baseball glove, or you can get its mirror image, a right-hand baseball glove, and a glove designed to fit on your left hand will not fit on your right hand. Other things that are chiral, shoes are chiral. Shoes are chiral because feet are chiral. So you cannot put your left shoe on your right foot. It just doesn't fit. Your foot is chiral, your shoe is chiral, therefore they don't interact the same. A left shoe will not react with a right foot the same as a left shoe will react with a left foot. You can get your foot in a left shoe. You can get your left foot in a left shoe. It's very difficult to get your left foot in a right shoe. It just doesn't fit correct. Note, by contrast, when you buy brand new pairs of socks, unless you're one of those freaks that have like toes built into your socks, that's crazy. It gives me the willies. Anyhow, if you have just regular socks, note socks are not chiral. Socks fit both feet equally. Brand new pair of socks that you can fit on either foot. So it doesn't matter if it's your left foot or your right foot. Your left foot's chiral, your right foot's chiral. But since socks are not chiral, socks interact with both feet equally. A brand new pair of socks will. So two enantiomers, when they react with non-chiral molecules, react the same with non-chiral molecules. However, the two different enantiomers react differently with chiral molecules. So that's the first thing. Enantiomers react differently with chiral molecules. The other thing is the two enantiomers rotate the plane of plane polarized light in different directions, which means we say they are optically active because they actually do rotate the plane of plane polarized light. And this can be seen with a polarimeter. Okay. I don't have a drawing here, so let me just quickly draw the basics of a polarimeter. All right. So what you have, you need a source of light, just a source of light like a light bulb. So there you have a light bulb. shining light in all directions. You make that light go through a polarizing filter. It is just basically a piece of film that has very dark lines etched very, very close together. Because light, when it comes out of a light bulb, some of the light waves are going up and down like this. Some of them are kind of going side to side, a little difficult to see. Say this is your eyeball looking at this light coming at it. What we're saying is some of this light is oscillating up and down, up and down. Some of it's oscillating side to side. Some of it's oscillating at a 45-degree angle this way. Some's a 45-degree angle that way. In fact, it's oscillating, going up and down like a wave at every possible angle through here. What this filter does is just make sure that all the light that is coming through is only the up and down light, only light that's oscillating up and down, towards the sky, down towards the ground, towards the sky, down towards the ground. It blocks out all of the others, essentially. And so then it's only up and down light coming through this filter. We then make it go through what we call a slit, just this tiny little opening here. We attach that to a hollow tube. And then what you're going to do is look with your eye here down along this hollow tube. You're going to be looking through this tube. All right. If this tube is empty, what will you see? Well, the tube is, when you're looking at it, it looks like a circle. And you're going to see, oh, there's a little beam, a vertical beam of light. It's this little vertical beam of light shining that you can see here because the up and down light is going through this vertical little slit here. So the shape of this slit is what you see. It'll be dark here, but here it will be a beam of light up and down because that's how you made the light go with this little opening. Okay, here's the fun thing. What if you put in let's go with the R, or no, let's just go with 1 enantiomer. You put the 1 enantiomer into the tube. So you fill this tube up with a solution that has only one of the enantiomers in there. What we then see is that beam of light has been rotated. It should have been straight up and down. The slit didn't rotate here. The slit is still going straight up and down. The beam should still be going straight up and down, but it's not. It has been rotated, excuse me, by some angle alpha, away from straight up and down. What happens if you put in the other enantiomer? Well, you put in the other enantiomer instead of being straight down. Note, you take out the first enantiomer, empty the tube, then put in a solution that only has the other enantiomer in it. The beam gets rotated the opposite way by the same angle alpha, but in the opposite direction. All right. So the empty tube, if there's nothing in there, there's nothing to rotate this plane polarized light. The slit was up and down, therefore the light that you see is up and down. You put in 1 enantiomer, what's it saying? As the light is going through here, it goes from up and down to start going side to side. It starts up and down, but then instead of keeping straight up and down, it starts rotating side to side. The further it goes through the tube, the more molecules it interacts, the more side to side it goes. So if you're looking through the tube, even though it starts out up and down, then it goes this way, side to side, like that, till you finally see what's coming out the end. You only see the result at the end. You don't see it actually rotating through the tube, you only see the end result. Okay, so 1 enantiomer rotates the plane polarized light one direction to the right. If it rotates it to the right, we call this dextrorotatory. And we label that the D isomer. If it rotates it to the left, this is levorotatory. And we indicate that's the L, lowercase l, enantiomer. What if you had a 50-50 mixture of the two enantiomers? Note, if you had an exact 50-50 mixture of the two enantiomers, when the plane polarized light interacts with one of the enantiomers, it wants to rotate it to the right, but then if it then hits the other enantiomer, that's going to make it rotate back to the left. A 50-50 mixture of the two enantiomers gives us the same result as if the tube is empty, no rotation. Okay. So if there's no rotation, we call this 50-50 mixture of two enantiomers a racemic mixture. A racemic mixture is a 50-50 mixture of the two enantiomers, and it does not rotate plane polarized light. Okay. Now, it turns out in chemistry this can be a bit of a problem, because when you make a molecule, when you make a stereo center, if you have a carbon that is not chiral and through your reaction you turn it into a chiral carbon, we're going to find out that means that you do make a racemic mixture. You make a 50-50 mixture of the two enantiomers. The problem is you only wanted one of those enantiomers, because the other enantiomer is probably not going to do what you want it to do. It turns out a lot of the proteins, a lot of the enzymes in your body are chiral, and therefore only one enantiomer is going to fit in there. So if you want to take a medicine that's going to make you feel better, it has to be the right chirality. It has to be the correct enantiomer. If it's the wrong enantiomer, usually nothing happens, but occasionally bad things will happen with the wrong enantiomer. So a big problem in chemistry is you only want one enantiomer, but in a lot of the times when you make chiral carbons, you get a racemic mixture. You get both enantiomers you then have to separate. And how do you separate those two enantiomers from each other? Well, you can't use extraction with regular solvents because the two enantiomers react the same with regular solvents. You can't distill them. You can't because they have the same boiling point. They have the same melting point. They have the same solubilities. They have the same densities. So you really have to find other chiral molecules that they will react with to try to react one of them to get rid of it. It is a pain and it is expensive. Okay. So here we have our deal. Empty tube, no rotation. If it rotates it to the right, we call that the dextrorotatory isomer. If it rotates it to the left, that's the levorotatory isomer. If you have a 50-50 mixture of the two enantiomers in the tube here, you'll get no rotation. We call that a racemic mixture. Okay. Looks good. All that has been explained down here also. So, how many degrees of rotation will you get? How much will it rotate? Well, it depends on a number of factors. It depends on the concentration of the enantiomer. The more enantiomer you have, the more molecules the light will interact with, the more rotation you'll get. The length of the tube, the longer the tube is, the more molecules the light will hit. There's a nice equation that the specific rotation, which is a constant that you can measure, equals the observed rotation divided by the concentration of the solution times the length. So this rotational constant equals the observed rotation divided by the concentration times the length. Another way of looking at that is a constant such as epsilon equals the observed rotation, or here's observed absorbance, divided by the path length times concentration. This deal here, this equation for specific rotation, is essentially Beer's law. Instead of absorbance, we're looking at the angle of rotation that we see. Instead of the molar absorptivity, we're looking at the specific rotation, but we're still looking at the length of the tube, and we're looking at the concentration. Okay. Now, this also, since we're talking about light and its wave going up and down, it depends on a little bit on the wavelength of light used. So when you see your specific rotation, the alpha in the square brackets, you often see 25D. 25 because we're at 25 degrees Celsius, D because we're specifically looking at the light emitted when you pass a high voltage electricity through sodium. We call them the sodium D lines. They are two yellow emission lines when electricity goes through sodium gas. All right. So if you find a molecule that says its specific rotation is plus 3.12 degrees, that means at 25 degrees Celsius, using the sodium D line emission, the wavelength of that is 589.6 nanometers. If you have 1 gram per milliliter of sample in a 1 decimeter long tube, the light was rotated clockwise by 3.14 degrees. All right. Examples for R2-butanol, the specific rotation is minus 13.52 degrees. S2-butanol, the rotation is plus 13.52 degrees. Now, this leads us to another issue. This is R2-butanol, and note that this is a negative here. Negative means levorotatory. Negative equals L. Positive equals D. So if we go back to this diagram here, dextrorotatory is D or plus, levorotatory is L or minus. But here's the thing, very, very, very important. What do plus and minus, what do L and D, what do D and L have to do with R and S? The answer is nothing. It turns out for R2-butanol, the R isomer is the L isomer. It may actually be the case that for R2-chlorobutane, if we just take that OH off of the butanol and put a chlorine on there, it could be R2-chlorobutane, might be the D isomer, might not be the L, it might be the D. R and S simply tell us, based on the way we drew it on the molecule on the page, which isomer is which. D and L tell us a physical property, optical rotation, but there's no link between R and S and D and L. The S isomer could be D, the S isomer could have been L. You just don't know until you put that in there. The one thing you do know, though, if you happen to know, if I had written down, okay, R2-butanol was L, we then would know, oh, if R2-butanol, if we know that that is L, then we also know that the S2-butanol has to be D. Because if R is L, S has to be D, because you can only have R and S, you can only have L and D. If you know R is one rotates in a certain direction, you know that the S rotates at the other direction. Oftentimes, but not always, we incorporate the plus and minus rotation into the names. So for this molecule here, this would be R-plus-2-methyl-1-butanol. So we know it's R because that's our conangled Prelog nomenclature. Plus tells us that it is dextrorotatory. All right. Note, here is R minus 1-chloro-2-methylbutane. Turns out, yeah, if you just take the OH and put a chlorine on instead, then the R isomer is actually the levorotatory isomer. All right. So, video's going a little bit long, but I want to mention one other thing. We've noted this before. There's no correlation between R and S and plus and minus. We just talked about that. Racemic mixtures, no rotation of the plane polarized light. There's something called enantiomeric excess. It means the percent enantiomeric excess is the moles of one enantiomer minus the moles of the other divided by the total moles of both. You can also get it by the observed rotation divided by the specific rotation of the pure enantiomer. All right. We're not going to get into it. Some people really get jazzed by enantiomeric excess. I'm not one of those people. What it means is this. Say you had a solution that had 75% R, 75% R, 25% S. What is the percent enantiomeric excess? Well, here's the deal. If 75% of it is R, 25% of it is S, this 25% that is S is going to counteract 25% of the R as a racemic mixture, which means we have 50% of the R left over. Yes, 75% of the molecules were the R isomer, but 25% formed a racemic mixture with S, giving us 50% of the R left over, so 50% is the enantiomeric excess of the R isomer. Enantiomeric excess is how much do you have of that isomer more than a racemic mixture. So what if you had something that was, say, 90% enantiomeric excess? The question is, what's the percent, it's going 90% enantiomeric excess of S. What's the percent S? What's the percent R? Well, if you have 90% excess of S, that means you had 10% of the solution is a racemic mixture. If you had 90% extra S, that gives you 10% racemic mixture. If 10% is racemic, that means you have 5% R and 5% S, because you have to have the same amount of S and R in racemic mixture, which means your total is the 90% enantiomeric excess of S plus the 5% of the racemic mixture. You had 95% S, 5% R. So this is as far as we're going to go with an enantiomeric excess. Just note that if given the two percentages, calculate the percent enantiomeric excess by knowing that whatever you have less of, that same percentage is going to be in a racemic mixture with the one you have more of. If given the percent enantiomeric excess, realize that's the extra, the rest is racemic mixture, divide that in two, and then you get your percentages. All right, that is it for our optical activity currently.